Last talk of this year's OSDI, I'm going to tell you something about the costs and benefits of implementing containers on microkernels with our approach called MettEagle. So I think the majority of you have heard of containers and have even used them. So what can we tell about them? Well, one of the most important features of containers is that they offer you a lightweight virtualization of different user space instances on top of a shared kernel. As such, they provide you with better security compared to standard processes on monolithic systems. And that's why they are a favorable choice to use in settings where you have to host multiple applications of untrusted clients on the same system. And how do containers implement increased security compared to standard processes? Well, they do so by adding new kernel mechanisms, and we can group these mechanisms into three categories. First, we have interface restrictions. Interface restrictions are required because processes on monolithic systems are able to exercise ambient authority, which means that, for instance, applications can access system calls that they do not need in order to execute their code in the first place. And interface restrictions try to reduce the attack surface that a kernel exposes by narrowing the set of interfaces or system calls that is available to a container to only the system calls that it actually needs. Second, visibility restrictions like Linux namespaces try to get rid of global namespaces that exist on monolithic kernels, for instance, for things like process IDs or network interfaces, to provide a more complete isolation of applications running inside the containers. And lastly, we have resource restrictions which enable administrators to set fine-grained restrictions on the amount of resources that a container consumes, and this might apply to a variety of resources, for instance, network bandwidth or the memory consumed. On top of the kernel, there is a container runtime running in user space, providing you with all the convenience tooling that you are used to, for instance, container image management and lifetime management of a container. So now let's look at containers from a security perspective. What can we say about them here? So this is an architectural sketch of a container architecture on a monolith. And obviously, containers interact with the kernel through the system call interface, and the kernel, like Linux, they implement a variety of functionality, for instance, memory management, file system, network stack, and so on. And also, there are plenty of drivers running inside the kernel. And with containers, what's happening now, that we have to add another layers of security mechanisms to the kernel. And these security mechanisms themselves are very complex, and we find ourselves in the paradox situation that even though those mechanisms try to increase security, they actually also are prone to security-related bugs, as we have also shown in the paper, where we analyzed past CVEs related to container isolation mechanisms. Also, a monolithic kernel has the classic deficits of monoliths. So it's easy for a fault, for instance, in one of the subsystems, like the file system, to propagate and compromise the whole kernel. And also, the size of the kernel makes it hard to reason about it as part of a certification process, which is a desirable thing to have when running your operating system in security-critical applications, for instance, automotive or aerospace industries. Lastly, another disadvantage from a security perspective is that containers or monoliths have a huge trusted computing base for both availability as well as security. And this means, for instance, that if there's a driver loaded in the system that is only used by one container, this driver still is in the TCB of every container running on the system, which is obviously something undesirable to have. So we believe that we can actually do much better from a security perspective. And this is a bold claim. So how can we do much better? We can do much better by building containers not on a monolithic kernel, but rather on a microkernel, like L4E in this example. Microkernels like L4E enforce the principle of least authority by design. And one cornerstone of this polar by design approach is the use of so-called capability-based access control. Capability-based access control means that every access right has to be configured explicitly, and you can think of a capability as an unforgeable token of authority that grants the processing process the power to carry out certain operations. And such operations could, for instance, be access of a memory page or a communication to another process via inter-process communication mechanisms. Another question is, how can we implement these 3 pillars of container-style isolation on top of a microkernel that uses capabilities? So first, the neat thing is that for interface restrictions, we do not need to do anything. And that's because if you do not want the container to access a certain interface, simply don't hand it the respective capability. The same thing goes for visibility restrictions, because microkernels like L4E do not have any global namespaces, for instance, for process IDs or anything. Such things do not exist. And thus, the visibility restrictions that we have to program into a kernel like Linux in hindsight are implicitly given by the capability system. So if a container does not possess a capability to a certain subsystem, it is not even aware of its existence. Lastly, resource restrictions are a bit more involved. So for these type of restrictions, we have to implement them in each system service in user space as we would have to do in each kernel subsystem in Linux with C groups. It's essentially the same effort to do so. However, also on L4, we have a unified API that at least facilitates the adoption of such resource restriction mechanisms. Okay, so what do we gain in terms of security when using containers built on microkernel instead of containers built on a monolith? First of all, we gain the advantages we gain by capabilities. So all permissions and visibilities are configured explicitly by the administrators, and there is no need to introduce complex in-kernel mechanisms in order to provide container-grade isolation to applications. We also profit from these traditional microkernel benefits, mainly fault containment in user space services. So since the majority of system services is implemented as user space processes, faults cannot easily propagate. For instance, if there's a security bug in the file system, it cannot easily propagate to the network stack. Third, by relying on the microkernel, we reduce the overall attack surface of the base system. And also the microkernel can be more easily certified due to its small size. And for instance, L4E here is certified for various standards, namely NATO secret certification as well as Eisoldt B or common criteria EAL4. And lastly, another advantage of running containers on a microkernel is that the containers TCB for both security as well as availability is minimal, meaning that only components that are used by a container actually contribute to its TCB. I would like you to redirect you to the paper for a more thorough security analysis, where we also compare the trusted computing base of both approaches, also do a CVE analysis and discuss resilience of microkernels against other classes of attacks. So until now, this is a very neat theoretical concept. So containers and microkernels appear to be a perfect fit. But of course, in order to use this in practice and also to get an OSDI paper accepted, we have to prove that it works in practice. And this is where the fun starts. Yeah? So what do we have to do in order to prove our point here? So we started implementing MettEagle, and at the very first, we just took the base system of L4E as is from the website. Unfortunately, we only had to do small modifications to the base system, so the L4E microkernel and the basic user space components, mainly the init process. And these modifications mainly extended to making it run on server-grade CPUs, all of those Intel Xeon line, and to do minor scalability improvements, but all in a small 3-digit number of lines of code changes. We then implemented from scratch something that is needed in order to provide meaningful services to container, namely a small in-memory file system, as well as a network stack with a driver and a simple UDP IP stack. And on top of this, we then implemented MettEagle, so the basic container runtime, as well as Flocks, a function as a service server that we will use in the benchmarks later on. So when running on large machines, performance was not sufficient with this setup, so we decided to further implement more scalable versions of both the memory management, called here the large-scale memory manager, as well as the bootfs that hosts binaries for applications and so on. And on top of all that, we run our containers, which are then nothing more than simple processes on a microkernel. But we still need to, in order to provide meaningful benchmarks, we still need a standardized write time. And in order to do so, we decided to port Python 3 to L4RE, which is very useful so that we can execute benchmarks written for other serverless platforms, as we will see soon. Okay, now enough of these abstract boxes. How does the system perform in a real-world scenario? So we benchmarked MettEagle on a standard server machine, a dual-socket machine with 64 cores in total. And we compared it against Linux processes, which provide less isolation, but can be seen as an optimal baseline with respect to performance. We also compared our approach to RunC, which is the OSDI-compliant standard implementation of containers on Linux, as well as Cutter together with Firecracker, which is a slightly different isolation mechanism which builds on lightweight virtual machines. And what you can see here in this plot is the plot of a cold start latency benchmark. You can see a cumulative distribution plot of the startup time in milliseconds. And fortunately for us, the cold start latency of a container on L4E is somewhat in the region of the cold start latency of a Linux process. So it's a bit worse, but it's still much better than the cold start latency of standard Linux containers as well as lightweight virtual machines. We then increased the parallelism, so starting 8 containers strictly in parallel. And what you can see here is that our approach still outperforms the cold start latency of our competitors on Linux, but that the gap between RunC and our MettEagle becomes smaller. And when we further increase parallelism here, so to the maximum number of cores in the system, you can see that this trend continues, and it's actually a major insight that this is due to coarse-grained locking inside the L4E microkernel. So even for a microkernel, it turned out that in order to achieve good performance and scalability on large machines, fine-grained locking of data structure is key. Okay, having said that, let's look into an application benchmark. To this end, we used ZEPS, which is a standard benchmark to test serverless implementations of cloud providers. And the way we changed the setup is that we had 2 machines, so one running Linux with the ZEPS benchmark client. And this client then sends Python code snippets to function as a service server, which may run L4 or our competitors for comparison. And on L4E here in this case with logs, the server then executes this Python script on behalf of the client and sends back the results. And why is Python a good choice for benchmarking? Well, it's because Python is actually quite a demanding workload for a microkernel because it heavily stresses the I/O subsystem, and microkernels tend or have the reputation of having performance difficulties with these things. So we thought that Python could be somewhat seen as a worst-case example with respect to performance. But fortunately, also here for a sequential function as a service benchmark, we can see that L4E is quite competitive with other approaches like RunC or Firecracker. What you can see here in the plot is on the y-axis the end-to-end latency of the serverless infrastructure in milliseconds, and on the x-axis you see different benchmark types. So we have a benchmark for HTML generation, a benchmark for file compression, and several graph processing benchmarks with varying problem sizes, which are indicated by those tiny suffix, or if it's missing, then it's a standard problem size. And when looking at the HTML generation benchmark, you can find that our approach even slightly outperforms Linux containers with respect to end-to-end latency. For the graph processing benchmarks, the performance tax of L4E is between 5 and 15% compared to Linux containers. And the only exception where L4E performs a bit worse is the file compression benchmark, and this is due to the unoptimized in-memory file system that we had to use for our benchmarks in order to work, or in order to run them. And it's also noteworthy that in all cases we are considerably faster than a serverless runtime which relies on Firecracker or lightweight virtual machines in order to isolate the containers or the Python scripts running on it. Okay, so in summary, what do containers and microkernels give us? So containers and microkernels provide us with a more secure, container infrastructure compared to implementing and running containers on monoliths. It's actually a very lean design because the very principles of microkernels quite support the implementation of containers quite well. And you also gain a lot of modularity with all those user space system services. Lastly, we can state that the performance overhead of implementing or of a container infrastructure on microkernels is actually quite low, even for highly dynamic workloads on server-grade machines. I would also like you to point you to our artifact. So the artifact, all the code is available online. You can either check out the base system, so the point where we started our journey, as well as the artifact of our paper that you can find on Zenodo. And with that, I would be happy to take any questions. Thank you.